All right, welcome. In AP Physics C, we have to start right off the bat with scalars and vectors, which is really math. And in 1.2, though, we get into actual physics. And physics is going to be concerned with the motion and interactions of objects. So right out of the gate, we have to start with where is an object located and how do we measure then how far it goes, which allows us then to talk about how quickly it moves between two different points. And then we can get into how quickly it speeds up or slows down potentially between those 2 points. So we're going to start with the basics here. Position is referred to as where an object is or its location. So you could think of it as the x value along like an x-axis or the y value along a y-axis, assuming that those are going to be meters. We already talked about displacement as being the change in x, and that does have a direction along some axis. So this is all spelled out here. For physics, we're going to be using the units of meters. We're not going to use feet or miles or inches or any of that stuff. We can use centimeters because it's really just metric prefixes. It's still part of meters. Centimeters would just mean there's 100 centimeters in 1 meter, but we're not going to be doing conversions between inches, feet, and miles. So the position is an instantaneous point. It refers to a location or point on an axis. This can be on an x-axis or it can be on an x and y-axis if we have 2 dimensions, which would require us to have a grid and we have a coordinate point, right, for that position. It would be like an xy coordinate point. If you travel between 2 positions, like a starting position and an ending position on an axis or grid, then that would be technically the displacement. We did talk already about how displacement is the straight line distance and arrow, since it's a vector, between point A and point B, a beginning and ending point, right? So that's going to be what we're going to be using for our how far is the vector for distance, which we actually refer to as displacement. So we do have to make sure we understand the difference between distance and displacement, right? So I'm going to give you an example here. Let's say an object starts at point A, moves 10 meters to the right, but then changes direction, heads back 2 meters, where it ends at what we could call point B. So from point A to point B, we could draw as a diagram right here, which is on your sheet. So it goes to the right 10, back 2, and we can see that the total distance that travels would be 12. That would be like the mileage you put on the car, so to speak. Like how far did you actually do? Your step count would reflect that you went 12 meters because you went 10, and then you turned around and walked in addition 2 in the opposite direction. That would be the distance traveled. Nothing wrong with that, but we're often in physics concerned with the vector quantities. So if we did want to stick with the displacement, then we would end up with the overall displaced distance, right? Which would mean like how far did you end up from where you started? Started at A, ended up at B. How far is B from A? 8 meters. And you can easily see how I got that from the diagram, but we would just simply be adding up those 2 vector quantities, the 10 meters to the right, so positive 10, and then 2 meters to the left, so we have to make that negative 2. And then when you add those up, you get positive 8. Just vocabulary-wise, the initial position, what we were calling point A and point B, is typically going to be referred to as an initial x value, or what we can call an initial position. So that would be x naught. Anytime you put a little 0 as a subscript there, that is going to make it the initial version of that variable. So it's the initial state that it's in when time 0 occurs, and we would call it naught. It's a British term for nothing. So it's x nothing, or what we can call x naught. So x naught would be the initial position, and we would just use x as being the ending position that it has sometime later. So the change in position from point A to point B would actually be referred to as the change in position from x naught to x. So how did we go ahead and get that displacement as an equation? Just like we did up here when we did 10 plus 2, right? Or if we wanted to figure out where we ended up, if it were at a distance of 8 and we started at 0, we would do 8 minus 0, right? It would be where you end up versus where you started. This would also be the same thing, let's say if we started at 5 and then we ended up at 13. We would take our ending value of 13 minus our beginning value of 5, and we would again get the same delta x using our displacement equation. So if we start talking about how quickly we travel some displacement, then we're going to get into velocity. And there's two ways we can refer to the velocity. It would be what is it on average, or what is it at some moment in time or an instant in time, which we would refer to then as instantaneous velocity. They're both vectors because velocity is a vector. So it's going to be meters per second is going to be the standard units. And let's take a look at what we have here. So average velocity would refer to the average rate of change. This would just be the overall displacement between 2 points and how much time did it take to get that displacement traveled. So from an algebraic standpoint, this would be the change in meters over the change in seconds. That's going to give you the average. Now, if you were speeding up or slowing down, then that wouldn't give you the instantaneous value because it's changing throughout that duration of time. So it would just give you the average over that entire time. If we look at a graph, which we will later, then this would be the slope, right? Giving us like a rise over run. And you can pick any 2 points in the curve. So this would be what in pre-cal we refer to as the slope of a secant line, which would be the line connecting 2 points on a curve. So look at some random graph here. This is an example of a quadratic. Then I may have 2 points on here. It could be 0, and it could be out here at 15. It could be some point 5, and then the time is 20. But so at some point here, I'm going to call it point P right here at 5. And let's pick another point like out here at Q. Now, if I wanted to look at the secant line between these, I would be drawing a straight line between them, right? And that's going to then give me a straight line whose slope is the average velocity. Notice that the velocity is not exactly, meaning the steepness, is not exactly this steepness the whole way because it's curved. But if we just take an average, then that would be what the speed would be over the entire 5 to about 15 seconds. Instantaneous would be wanting to know what is the speed right at point P. So essentially we would have to shrink down this P to Q distance to be essentially the same point, and you can see here this would now be the slope of a tangent line at P, and we can change this to be at any point, and you can see here it's getting steeper. So this would be looking at the slope at a single point, and it's the slope then of what we would refer to in math as a tangent line. And that's really from a graphical standpoint the difference between an average velocity and an instantaneous velocity is the average velocity would be the slope of that secant line between 2 points in the curve, whereas instantaneous velocity would be the slope of a tangent line that's at a single point on the curve. In order to do this, we would mathematically, algebra is all we need for average velocity, which is what we did a lot with ninth grade stuff. But now that we have calculus, we're going to be looking at the instantaneous velocity by squeezing down that P to Q interval to essentially be a single point. And that can give us the slope of the tangent line. And there's some calculus techniques that we discussed already that allow us to do that. And looking at a couple examples here, we'll first look at the difference between speed and velocity and then get back into the average versus instantaneous that we were just talking about. So with speed versus velocity, we have to make sure that we're using this concept of scalars and vectors that we discussed in the previous video. And so we're going to use that same distance situation that we had where we went 10 to the right and then we went 2 backwards. So from a distance standpoint, that was a total of 12 meters. And that's what we're going to use if we want to know the average speed, meaning the scalar quantity, because we ended up going a total of 12 meters. And in this problem, it's saying that it took 5 seconds to get all the way to the right, those 10 meters, and then it took an additional 4 seconds to get those 2 meters backward. So that totals 9 seconds, 5 there and then 4 back. So the total of 12 meters that we traveled occurred over 9 seconds, and that gives us an average speed as a rate of change, right, for meters over seconds to be 1.33. If we wanted to look at the average velocity over this entire duration, then we would want to use the displacement that occurred over time. So effectively, because we went too far and then came back, we ended up only really going 8 meters over those 9 seconds. So that was averaging out to 0.89 meters per second. Let's take a look at example 3 now. This is going to be related to the average versus instantaneous velocity. So in this problem, we have an object's position along an x-axis that's going to be plotted as a function of time. So it's a little confusing, but the position would be along this y-axis here, and the time would be along the x-axis here. We want to determine its average velocity between the time of 2 seconds, which is right here. At 2 seconds, it's located at a position of 16 meters, until a time of 8 seconds, which is over here. And at 8 seconds, it's going to be located at 160 meters. So when we do this, we're going to be looking at slope of this line. So the rise would be 160 minus 16 over the run, which is 8 minus 2. So how far did it go? We have to take the difference of 160 minus 16. That's its displacement. And then how many seconds did it take? 6 seconds. When we do that, we get 24 meters per second. Now we're going to take the same curve here, and in part B, we want to estimate its instantaneous velocity at time equals 6. So that's at this point right here. Now its position is 96. And I can see here I drew this tangent line in for you, this blue tangent line. So the question would be, what is this instantaneous speed? And what we'd essentially be doing here now is getting the slope of this tangent line. So I got to pick one point on here aside from 696, right? At 6 seconds, it's at a position of 96. So I got to pick any other point along that blue line that I can estimate its coordinate point or coordinate values. And so I'm going to use this one right here. So at 4 seconds, it looks like it's approximately 40 meters. And so now I can do rise over run there, and I can get then the velocity at times 6 would be equal to 28. And I got that by doing 96 minus 40 divided by 6 minus 4. And that gives me my instantaneous speed. We can also do this instead of graphically, we can do it just with math and functions. And so what we're going to now need instead of the graph is the function that describes that parabola. So this is the same exact situation. These are all the same parabola. And if I get the function for this parabola, it would be 4t plus 2t squared. Now, if I didn't have these graphs, how could I go ahead and get the average velocity, instantaneous velocity, like I did in the previous ones where I did have the graph? So average velocity, remember, that's going to require algebra, right? Algebra, because it's an average rate of change, and so that's just algebraic. Instantaneous is when we need to use calculus, and in particular, derivative when we want an instantaneous rate of change, slope of a tangent line. So algebra is average, calculus is instantaneous. So in terms of what we're going to need to do for part A, since it's average velocity, we should only need algebra, and so I just need to figure out, well, where is it at x0 and x? And so since I didn't know those coordinate points, I need to go ahead and figure out what was its position at 8 seconds and 2 seconds so that I can do the difference between those two locations to get my displacement. So that's going to then allow me to do my equation for average velocity, which is the displacement divided by the change in time. And using the two values I have for my ending position and my initial position, I can then get the same math that I did when I tried to get the slope in the graph up here. So this was just given graphs. Let's use some graphical techniques like slope. And if you're given a function or constants, then we want to stick to using algebra and calculus. In this case, we only needed algebra, but in part B, since it wants instantaneous velocity, we're going to need to use calculus. And so in that case, then we're going to use, instead of delta x over delta t, we're going to use dx dt, which is the notation for an instantaneous, or a tiny, tiny delta x and a tiny, tiny delta t, meaning they're essentially shrunk down to being a single point. So the delta x is not even measurable because they're so close together. So this is going to be the notation for doing a derivative. And when we do the derivative of this for t, we would do, remember it's t to the first power, so that 1 comes out in front. We subtract then 1, so that gives t to the 0. T to the 0 is 1, so left just with 4. In the second term, we're going to multiply that square, that 2. We're going to take that 2 out in front. 2 times 2 is 4. And then we're going to reduce the power by 1, which is just t to the first power, and that leaves us with 4t. When we substitute in a time of 6 into this function, we get our value of 28. All right, hope this helps. Thanks.